Hey friends, so today we're going to be talking about systems of equations using a different method. For the past 2 days we've been working on solving systems of equations by graphing. And it was really nice because both of our equations were in slope-intercept form, so we were able to plot that y-intercept, use the slope, and we could see their point of intersection. So it's not always going to be given to you like that though. You may have two equations where only one of them is in slope-intercept form and the other one is in something called standard form, or maybe even something different. So I wanted to show you a new method of solving a systems of equation. This method is called substitution. Whenever I think about substitution, I sometimes think of a sport. I played basketball whenever I was in high school, and whenever we would use substitutes, it would be somebody else that played the exact same role or the exact same position. So if I were going in as a post player, I wouldn't be the one dribbling the ball down the court. I would be taking the place of the other post player, giving her a break, right? So kind of think about that whenever we're talking about substitution. They have the same role, okay? So just a quick refresher, a system of equations is whenever you're given two or more equations using the same variables. A solution to that system of equations is the ordered pair, x comma y, that makes both of those equations true, okay? The best time to use substitution is whenever you have one of your variables isolated. It doesn't matter if it's x or y, but if you have one equation where there's a variable isolated, that's the best time to use substitution. So what we're going to do now is we're going to work through some examples. I'm going to be reading the steps as we walk through those examples. That way you can kind of understand how to use the steps as you're working, okay? Turn that off. Like I said in our last video, I am going to be using two separate colors. That way you can kind of see what I'm plugging into where. I'm going to be using arrows quite a bit as well, but hopefully using the two different colors will help you see what those arrows are doing. In our first example, we're going to have y equals 2x minus 1. Our second equation, we're going to have 3x plus 2y equals 26. So hopefully here you can see what I mean by one variable being isolated. Right now, we've got the y isolated in this top equation. You can see in this bottom equation, it's not like that. This problem is set up for substitution. What we're going to do, step one says isolate one of the variables. It's already done for us, so we get to move to step two. Substitute the expression from step one into the other equation. So right here, they're telling me what y equals. Y equals 2x minus 1. So I can take this expression and substitute it in right there for y. And here's what that does. 3x plus 2 times, what are we subbing in for y? This expression up here. 2x minus 1 equals 26. So right underneath that it says the new equation should only have one variable. And look, it only has x's. It doesn't have any y's. Step 3, solve the new equation. Well, my first step would be the distributive property. I would distribute this 2, and I would get 3x plus 4x minus 2 equals 26. I can combine these two because they're like terms. We'd get 7x minus 2 equals 26. Add 2 to both sides. 7x equals 28. Divide by 7. I don't know if you guys can still even see that. We get x equals 4. And it says, this gives you one of the coordinates. I found my x. So now, step number 4 says substitute the result of step 3 into one of your original equations. So I can take what I found x to be and plug it in right up there. And I get y equals 2 times 4, because that's what x equaled, minus 1. And so I get 8 minus 1, y equals 7. Remember, my solution should look like an ordered pair, x comma y. So that's how we write our answer. 4, 7. And that's a solution to our system of equations, okay? We're gonna work a lot more together, so don't panic if you're like, holy cow. And I mean, look at this. This is a lot more work than what we have been doing. Take your time. Make sure that you're checking for your negatives. Make sure you're not making any silly mistakes whenever it comes to addition and multiplication and all that kind of stuff, okay? So let's look at another one. Let's say that we're given negative 4x plus y equals 6 and negative 5x minus y equals 21. I don't know if you noticed, I don't have one that's isolated this time. I do see that this y is positive and it already doesn't have a coefficient. It doesn't have a number in front of it. So it'd be pretty easy to isolate y. Let's go ahead and do that. The way that I move this 4x is I add 4x to both sides. And now I end up with y equals 4x plus 6. These aren't like terms, so I can't combine them. So I just have y equals 4x plus 6. Now that I have a variable isolated, I can continue with substitution. This is what y equals, so I can take this expression right here and plug it in for y. So I would have negative 5x minus 4x plus 6. Notice how I'm using parentheses to substitute that in. Equals 21. The reason these parentheses are so important is because now I have to distribute that negative sign through. I get negative 5x minus 4x minus 6 equals 21. Combine your like terms right here, and we get negative 9x minus 6 equals 21. Add 6 to both sides. Negative 9x equals 27. Last step. Divide both sides by negative 9. X equals negative 3. There's one of my coordinates. Now that we found one, we can take it and plug it into one of these original equations. I'm going to choose to plug it back into that one because it's already solved for y, and that's what I'm looking for. So I'm going to have y equals 4 times negative 3 plus 6. 4 times negative 3 is negative 12 plus 6, and we get y equals negative 6. So my solution is x comma y, so negative 3 comma negative 6. There's my solution. Okay? Let's look at another one. What if I have 6x plus 2y equals 0 and y equals negative 3x minus 4? I already have a variable isolated, so I don't have to do anything to isolate a variable. I can just plug it in. I know what y equals, so I can take this expression right here and plug it in for y. That leaves me with 6x plus 2 times, negative 3x minus 4 equals 0. Now I use my distributive property. 6x minus 6x minus 8 equals 0. When I combine my like terms, something happens. 6x minus 6x, what happens to them? They're gone, that's 0. So I'm left with negative 8 equals 0. Is that a true statement? No, negative 8 doesn't equal 0. Since this is not a true statement, that means that there is no solution. There is not an XY pair that could make both equations true. There's no solution. If we think back to yesterday's lesson, what would that mean about those lines? It means they're parallel. They have the same slope. They're never going to cross. No solution. Let's do one more together. Now then, before I erase that, something that I should mention, since this was not a true statement and it was a no solution, I can kind of use that. What if I had like -8 equals -8? What if I had that? Is that a true statement? Yes, it is. If it's a true statement, that would mean that there is infinite solutions. That's a big deal. So if it is a true statement, infinite solutions. If it's not a true statement, there is no solution. Okay? Now let's talk about our last example. Here we go. If I have 6x minus 7y equals -1, and x plus 3y equals -21. You can see here that I don't have a variable that is isolated. However, it looks like it would be really easy to isolate this x. It doesn't have a coefficient in front of it. It's already positive. All I have to do is subtract this 3y from both sides. So now I'm left with x equals -3y minus 21. They're not like terms, so I can't combine them, so I just list them out. I can take this expression and plug it in right here for x. So what that leaves me with, 6 times -3y minus 21 minus 7y equals -1. Use our distributive property here. So we get -18y minus 126 minus 7y equals -1. Here are like terms right here. And I get -25y minus 126 equals -1. Add 126 to both sides. -25y equals 125. Divide by -25. And we get y equals -5. Now that I have one of my coordinates, I can take that and plug it into one of my original expressions. I'm looking for x, so I'm going to plug it into one where I can find x. X equals -3 times -5 minus 21. Negative times a negative is a positive 15 minus 21, and we get x equals -6. So my ordered pair is -6, -5. And that's my solution. Guys, you can see here, there's a ton of work. There's a lot of arrows, there's a lot of plugging in, there's a lot of distributive property. Be so careful with your negative signs. Make sure that you're not missing one somewhere. Thankfully, our assignment is multiple choice, so you'll kind of be able to narrow that out. Don't just pick the one that's closest to it. Remember our ACT skills. They know what you're going to mess up on. They know if you're going to miss a negative or not. So if you missed it, go back through your work and see if you can find your mistake. If you can't, I would be honored to help you find it. Take a picture of it, text it to me, and we can kind of work through that issue together. Using substitution to solve systems of equations. Good luck, guys.